All right, so just a few things to talk about. I'll try to keep this brief here. One thing was I got hung up on this little calculation that the push forward under a coordinate map of the coordinate derivation should just be the corresponding Cartesian coordinate derivation down on the base in Rn. And so the proof of that, and so basically it's one of those things that John Lee's book doesn't introduce this notation. This just makes an identification, right? And but here's how you do it if you wanted to. So the push forward under the coordinate map of the coordinate derivation, by definition, is the coordinate derivation acting on g composed with phi. All right, by definition. So if we let f equal to the map g composed with phi, just for the sake of thinking through it, then we have this. All right, but then how did we define that? We define that to be the derivative with respect to the Cartesian variable of f composed with the inverse to the coordinate chart, right? Okay, well, what's that? Well, that's g composed with phi inverse. So these guys cancel, and you're just left back with partial g, partial ui, which, of course, this is an identity which holds for all g, right? Since it holds for all g, then we just simply get the push forward under the coordinate map of the coordinate derivation is the Cartesian coordinate derivation, aka, dx pushes partial x to partial u, if you like. So there's that. All right, so then the other thing I wanted to talk about in this video is just the explicit isomorphisms between the different versions of the tangent space, right? So we take the tangent space to be the derivations on the smooth functions at the point, right? That's following John Lee's book. But another viewpoint is the equivalence classes of curves based at the point. So let me talk about that for a bit here. So two equivalence classes, they're equal if they're that means these would be equal only if gamma 1 and gamma 2 are equivalent curves. The equivalence of these curves is judged by whether or not their derivatives match, and of course we're assuming that gamma 1 of 0 is equal to gamma 2 of 0, which is equal to p. All right, and so to prove that the isomorphism from the equivalence class of curves to the derivation, right, and where this is the derivation as we just defined at the end of chapter. Oh goodness gracious, give me a second here. The velocity vector. I left the formula over here. We talked about this, but here's the formula, right? So the velocity vector to the curve is defined to be the push forward of ddt under the differential of gamma acting on f, which basically just means that you're differentiating the composite of gamma under f with respect to time. In terms of coordinates, here's the actual, components of the vector that gamma prime t naught forms. All right, so there it is. Now, and then just to recap, of course, TPM is derivations on smooth functions, which means linear, and it obeys the product rule. All right, so on page 72, John Lee's text says a few things about the equivalence classes of curves. Like here's the basic definition: gamma 1 equivalent to gamma 2 if they we'll use 0 as the base time to match things up. So these would be equal to p, and the velocity vectors are equal. That's what we need for equivalence of the curves. All right, so let me get back to the other here. So the question then is, how on earth is the equivalence classes of curves equivalent to the derivations? And I claim the isomorphism is simply given by the velocity vector of the curve. All right, so now to prove that this is in fact an isomorphism, I first have to explain how on earth the equivalence classes of curves are a vector space, which is far from obvious. But let's see here. So actually we're going to come back here in a minute, first I'm going to explain how this is a vector space. So I think I have to skip 2 pages ahead, and then we'll come back here. So the vector space structure of the equivalence class of curves. Here's the basic idea. I've got, curve 1 here, and then its image down here like so, right? I've got curve 2 here, right? And then its image down here like so. So, we take the curve on the manifold, right? Up on the manifold here, and I'm looking at the corresponding coordinate curves down here in Rn. And so curves in Rn, we can do things down there that we know from calculus 3, advanced calculus, whatever you want to say. This is just Euclidean space, so we can do the usual stuff down there. And so if I look at the coordinate curves, gamma hat, gamma 1 hat, gamma 2 hat, notice that they're based at x of p, all right? And specifically, here's the formulas for them, right? Gamma 1, the velocity vector to the first curve is this, the velocity curve vector to the second curve is that. And my claim is that you can you can build a curve. I don't have another. You can put one right through there, right through the middle, whatever, right through that point again. Let's call it alpha hat. And alpha hat I'm going to build simply to be the line, which is based at x of p and parameterized by the sum of the 2 tangent vectors. And I'm throwing a constant in here just because I want to define the scalar multiplication and the vector addition all in one foul swoop. So this is a curve I can define down here. It's just a line. It's a line which by construction has direction vector, which is this velocity constant times this velocity plus that velocity as its direction vector. And of course, once I have that line, then I can take x inverse and map it back up to the manifold. And that's going to be exactly what I want to identify as essentially, that's going to, the velocity vector to that, the inverse image of the line up there is going to give me the vector, which is the constant times gamma. It's going to define the vector addition upstairs. And so here's how that goes. See, I lift the line gamma hat back up to m by x inverse composed with alpha hat here. That has alpha of 0, which is this, which is that, which is at p, so it goes through p, and by construction the derivative of alpha prime is this. All right, but what is that? Well, alpha is x inverse composed with x hat, so the you've got xi composed with x inverse composed with alpha hat. By the way, what this does is it picks off the ith Cartesian coordinate of that. It's a good thing to work through for yourself. Xi upper I composed with x inverse of u is equal to u upper I. So this is nothing more than selecting the ith component of the path down in Rn, which gives me that. And then I differentiate, and then this is just we're differentiating a parameterized line, so it gives us the direction vector, and that is what and that of course then by definition of addition of derivations is exactly c gamma 1 prime plus gamma 2 prime of 0. So this is how we're going to define the vector addition of equivalence classes of curves. It's a little bit circuitous, isn't it? So yeah, let me just finish that story here. So we have, this is the equivalence class of curves, a set of all equivalence classes of curves. And if we consider 2 equivalence classes, we can construct the line down in the image under the chart near P. And of course here the components of V1 and V2 are exactly the, they're what you get for the components of the velocity vector of 1 and the velocity vector of curve 2. Of course, to select the components, we just let the derivation act on the coordinate function xi. And then, so lo and behold, we define C times the first equivalence class plus the second equivalence class to be the equivalence class of alpha, where we define alpha as I described on the last page, x inverse composed with the line down in x view. So to see this is well defined, notice that because we're using equivalence classes of curves, right? So we should talk about why it's well defined a bit. If we used two different curves that represent these class, right, like gamma 1 equal gamma 3 and gamma 2 equivalent to gamma 4, and construct alpha 2 using these other representatives, well, then we'd have alpha 2 prime of 0 is this plus that. But then by the definition of equivalence, this is equal to that, and that's equal to that. So the equivalence class of alpha is equal to the equivalence class of alpha 2. See, it doesn't matter. If we used a different representative, we'd still get the same construction. We'd still get the same addition. So that makes the vector addition well defined. And you can run through the rest of the axioms to see that, in fact, this does give a vector space structure to the equivalence classes of curves. And this is why John Lee says that it's far from obvious how to define the vector space structure on this. I agree. So let's go back, now that we know how to do it. Why is it isomorphic to the derivations? So the reason, going back, is, all right, so I said psi of the equivalence class is gamma prime of 0, and so here we go. I take this plus that. That is equal to the equivalence class that we just defined and talked about, all right, where alpha prime of 0 is c gamma 1 prime of 0 plus gamma 2 prime of 0. So yeah, that's that. But then by definition of my isomorphism, that's that. So it's linear. Now we just got to show it's a bijection. So to see it's a bijection, if we take a derivation v, right, we can construct gamma of t like so, all right, and if we do that, x composed with gamma is this, and then if I map the equivalence class, so this is what this is a curve on the manifold, which is by construction the lift of a line down in Euclidean space, which takes v1, v2 to vn as its direction vector. So that essentially it's the same trick that we used to define the vector addition on the equivalence class of curves. And so that gives me that this, this is gamma prime of 0, but again, by construction, that is exactly v. So that shows that the linear map is surjective. And then what? And then, to see that it's injective, which is what we need to show it's a bijection, right? Injective, surjective, and linear gives us an isomorphism. Let's see here, so suppose we have psi of gamma 1 is psi of gamma 2. That gives us gamma 1 prime of 0 equals to gamma 2 prime of 0, but hey, by definition of the equivalence classes of curves being equivalent, that means gamma 1 is equivalent to gamma 2, because in context here, they're both going curves through P, right? Okay, fine. So therefore, psi is 1 to 1, which shows you that, in fact, that is an isomorphism. And the inverse is actually easy enough to write down. In fact, maybe we should invent some notation to put us out of our misery. We can say that psi inverse of the vector v is the equivalence class of curves, with direction vector v. In particular, gamma v of t, we can just be like it's the inverse image of the curve in Euclidean space with the direction vector v under the coordinate map. See, if I do that, that gives me, by construction, the curve which takes v as its velocity vector. So in this notation, the definition of the equivalence class of curves addition is simple to see. This plus that is really just that. So this notation makes the equivalence class of vector space structure easier to see through. And none of this is really different than what I said in class, which is that we're essentially just forcing the vector space structure through the bijection. The other viewpoint is the physics viewpoint, which is weirder. But the physics viewpoint, basically, to be completely honest, involves a triple: the point, the vector, the coordinate system. And so two triples are equivalent only if the points match up and if the vector components are related by the usual transformation law for a contravariant vector in physics. And So if we, and then define vector addition, you just keep the point steady and you add the vector parts. If you were to pick a different representative and you were to add in the different representatives, well, you get that, but then this is related to that in the natural way because, well, this is equal to that by the coordinate change rule, and then you can take this and that, you can factor it out, and you get this, which then shows that the triple with this coordinate representative is equivalent to the triple with that coordinate representative for the vector, because that's how they're supposed to change. In other words, this is equivalent to that, which then proves that the vector addition is well defined. And you can prove that it's a vector space over R. It's not especially interesting, but there it is. The isomorphism between the physics formalism and the derivations formalism is easier because you just, for a derivation, all you gotta do is basically strip off the components of the vector and stick them here, and that's it. It's easy to see that that's well defined, and it's simple enough to check that it's linear, like so, and the inverse map is simple to write down as well. That proves it's a bijection. So that's pretty much it. I could belabor these things more, but I think that's let's just kind of like a band-aid, rip it off and move on. So anyway, thanks guys. I appreciate your patience. Talk to you later.